Recording in progress.
Hi, today I'll be explaining the concept of an ICE table. An ICE, or initial change in equilibrium table, is used in order to simplify calculations in equilibrium and acid-base reactions. I will be going over two different types of ICE problems today, so let's get started. So the first problem we're going to be going over today is using an ICE table to determine Kc for the following balanced general reaction. 2x makes 3y plus 4z. So the initial concentration for x is 0.500 moles in 0.750 liters, and the equilibrium concentration is 0.350 moles. So what you're trying to find is Kc. So let's create the equilibrium calculation for this. So Kc has to equal, so that would equal y, the concentration of y cubed. Oh, 1 second, I'll erase it. Times z to the fourth over x squared. So with this, we have to then use an ICE table in order to calculate the concentrations of y and c to find Kc, which we are looking for. So let's get started. So let's do I, C, E. So I is the initial concentration, or what happens when you start the reaction. C is the change in concentration, and E is the equilibrium concentration. So you subtract the initial concentration from the equilibrium concentration in order to get the change. So the reaction would be 2x. 2x makes, this 3y and 4z. So the initial concentration for x is 0.500 moles. And then you have to, and the equilibrium concentration of x is 0.350 moles. In order to find the change in concentration, you have to subtract the 0.500 from the 0.350, so it becomes a minus 0.150. And this is for 2x. So you have to divide the 0.150 divided by 2, that makes 0.075. And this is like kinetics, where the reactants have a minus, and the products, as they're being formed for the duration of the reaction, they'll be added up. So there's 0y and 0z during the beginning. And this is for the initial. So initial is basically the beginning. And then you have to add. So as there's a 3 coefficient and a 4 coefficient, so you have to multiply 0.075 times 3, which would be 0.225. So plus 0.225. And then for z, it'll be 0.075 times 4, which will be a plus 0.300. And so the equilibrium concentration, well, the equilibrium amount of moles will be 0.275 and 0.300. Now we have to convert all of this into molarity. And so there's 0.750 liters. And to get molarity, you have to divide moles by liters. So you can use a calculator for this. So let's do 0.350 divided by 0.2 to get molarity of 0.467. And then for the second one, 0.275 divided by 0. Equals, and that would be 0.300 molarity. Actually, wait, it's sorry, 225, not 275, my bad. 300 molarity and 0.300 divided by 0.750 equals 0.4 molarity. You then use the Kc equation. So you do, so Kc will equal 0. Squared. Oh, sorry, 0.3 cubed and 0.4 to the fourth divided by 0.467 squared. So once you calculate that, then you get a Kc of 3.17. Ten to the negative third. So this is our answer for the first problem, because it's asking us to determine Kc. So I'll just wait a few seconds for copying this down. Then, yeah, so let's, 1 second, let's clear all drawings. Okay, so let's go to the next problem. So problem 2 is to calculate the hydroxide concentration and pH when you have 0.085 molarity sodium fluoride. So for this one, what you're trying to do is that you have to first create a calculation in order to get the equilibrium concentration. So let's do that first. So when you have NaF, so NaF is soluble in water. So it'll be Na plus F minus. And so we want the F minus, and we just want to take the Na out of this whole thing. So it'll be F minus plus H2O. And F minus is a base, makes HF plus hydroxide, OH minus. And then you have to calculate the KB. So KB will be HF, concentration of HF, concentration of hydroxide, over the concentration of F minus. And now that you have the concentration of F minus, which is 0.085 molarity, as NaF, there's only one Na and one F, the concentration of F minus would be 0.085. And so now you have to calculate Kb, and you can use a Kw equals Ka times Kb equals 1.0 times 10 to the negative 14th. So I'll be making another video on this, on acid-base stuff, so watch out for that. So Ka will be 6.8 times 10 to the negative 4. So you're trying to find Kb over here, so I'll get up another color. So Kb over here, this is what you're trying to find. So Kb would be Kb equals 1.0 times 10 to the negative 14th all over Ka. And Ka is 6.8 times 10 to the negative 4th. So you have to divide 1.0 by 6.8. And Kb, Kb will equal, it'll be 1.47 times 10 to the negative 11th. So this is what we're trying to use now. Now, as we have Kb equals HF, OH, and F minus, we have to construct a nice table in order to get like the hydroxide concentration, and then we can use that to get pH. So I'll erase all the stuff other than the Kb and the equation. So back to writing, and so now we have to construct a nice table. So I, C, E, straight line, and then we do the equation F minus plus H 2O makes HF plus hydroxide. So here, and then let's this like these problems can get a bit tedious at times, so this one the easier ones. So here, and so now what we have is we have to find the amount of HF. So you have 0.085 molarity HF molar, and you have 0 HF and 0 hydroxide. So you don't know anything else other than this over here. So we have to do then is that you have to just use X. So 0 plus X, 0 plus X, and minus X. And so what you get is 0.085 minus X. And it'll just be X, X. So then you just use this equation, which is 1.47, which is from here. So Kb is this. So 1.47 times 10 to the negative 11th equals X squared over 0.085 minus X. So So how could we calculate this from here? Because we have x squared and 0.085 minus x. You could use a quadratic equation in order to solve it, but then sometimes you don't have to if you know that the percent ionization is under 3%. So for percent ionization, it's basically if it's already, you can determine without having to use a quantitative analysis by seeing if the KB is very low, and it is because it's to the negative 11th, so it's like very small. So you can just, 1 second, you could just take out the x, so you don't need to ever, you don't have to use the x, so it'll just be 0.085. And then you just go and solve it like you would for a normal thing. And you basically get 1.47 times 10 to the negative 11th times 0.085, and then you square root it, equals x. And the answer for that would be 1.1 times 10 to the negative 6th equals x. And this is also the OH concentration. So as x is this, so OH equals 1.1 times 10 to the negative 6th. Now you just define POH, which is negative log of the hydroxide concentration. You just do negative log 1.1 times 10 to the negative 6, which then equals 5.95. And this, like, you should use a calculator because it is hard to calculate. So just 1 second, and then from this, you have to subtract 14 from 5.95 to get pH. And 14 minus 5.95 would finally equal 8.05. And that is our pH. So we got our hydroxide concentration, which is 1.1 times 10 to the negative 6th. And our pH, which is 8.05. So this is basically how you do it for almost all of these problems. And yeah, so 1 second, I'll just leave the drawings. So I guess for finding some more problems, I would just look around the internet and just see if your textbook has any also. But other than that, so thank you very much, and stay safe.